Hello, welcome back to Organic Chemistry. My name is Todd Rothman. In this video, we're going to go over the orbital description to get a little bit more details as to why staggered is more stable than eclipse. Okay, so at this point, we know it from the point of view of saying that eclipse has torsional energy and that staggered has some gauge, but it doesn't have torsional, right? But now we're going to go a little bit further into that torsional energy and learn a little bit more about how that works. Now, the first thing we need to do is describe just a very brief summary of a few things that we talked about from the previous videos, and also from exam 1 we're going to review the orbital. We have to get into a little bit of that. Now, the first thing I want to point out is, of course, eclipse we know has torsional strain. It has higher potential energy. It's more unstable in the torsion when it has more torsional strain, or when it's eclipsed, it's high in energy. Whereas when they're staggered, when the two groups of reference are anti or 180 from each other, remember anti is the reference of two things that are 180 apart, well, that's called staggered. And that is where the heat is released, right? So you could think about it like this. As we're going from eclipse, well, let's say staggered, and we go to eclipse, right now there's an increase in energy. The red carbons here, or atoms here, are starting to repel each other. And as you turn, now it releases that energy as heat. And so there's heat released, and then again energy, and then heat released, and so on. And so that's the idea of how this works. So we could think of staggered as more stable. Anytime you have heat being released, that means the system is becoming more stable. Anytime energy is absorbed, the system is becoming less stable. Okay? Now, the next thing I want to point out is the idea of why this would take place. And again, this is all review. Collisions is the key. Molecules collide, and when they collide, they rotate, they spin if it's a single bond. Now, if there was enough energy, actually, it would break a double bond, right? But in the case of single bonds, the collisions, these bouncing of molecules, makes them spin. And then, of course, the torsional strain, or when it overcomes the torsional barrier, it spins, and the torsional strain repels it even further to continue the flow of that spin. Now, if you lower temperature, as I mentioned in, again, the first video of this segment, we know that lowering the temperature reduces the collisions, which reduces the spinning. Okay, so eventually if you go low enough, you'll have them frozen in time, and most likely you'll catch them in a staggered, not an eclipse form. All right, now let's go over the review of orbitals. Now, the only thing I want to mention here, because we've done this, and if this is not clear to you, you could always go back to the orbital video. It's available to you to watch, and so make sure that, if this isn't clear, but this is just a review. Now, remember, we talk about having a hybridized orbital where it looks like a figure 8 type, remember, like the p orbital, but it's a fatter end and a thinner end to it. So we have these two lobes, and remember, these lobes represent the phases of this orbital. So if it's above its point of origin or below, and so we have these phases. Now, when the phases are the same and they come together, so here's an atom, here's another atomic orbital, and they're going to join together. When the phases match up, then you have what's called a sigma bonding MO, right? So this is where there's a larger area for electrons to travel. It's lower in energy. But simultaneously, while that's happening, you also get the anti-bonding. Now remember, when you have an electron, and so you have this one electron here and one electron there, they come together and they're going to go into the lower energy state, the bonding MO, the BMO, right? But there's also the sigma star, the anti-bonding. That's because the shades are not matching up. So if you look right here, there's a node because the phases are not the same. And notice that the larger area is in the opposite. So this is where the larger area is for the right orbital, and here's the larger area for the left orbital. So there's a very small area of space for electrons in between the two atoms. And so that's what we call a star, or an anti-bonding, or an ABMO, okay? So remember that whenever atomic orbitals come together, you always get these two. And also remember that if I look at a carbon bonded to some atom, let's say H, that when we draw on paper, this right here represents the sigma bond, but the sigma orbital. But what we don't see, but it exists, is that at the same time there's also an anti-bonding orbital. So for every bond that you see, there's actually two. There's the bonding MO, or for every bond, when you think of it from an orbital point of view, there's two. There's the bonding MO, and then there's the anti-bonding, which has no electrons in it, and that's higher in energy. Now, it turns out that for us to understand the idea of why eclipse and staggered are so much more or less stable relative to each other, eclipse being less stable, staggered being more, we have to think about the orbitals. So here's now taking the ideas from the previous page. If I have a carbon bonded to H twice, and I ask you to show me the orbitals that are bonding, I hope you could recognize that if H is shaded and the carbon's orbital shaded and they're matching, that's a bonding MO. So this represents a bonding MO for both of them. They have the shades matching up. Now, what if I want to see the anti-bonding MO for only one of them? So notice that this is still a bonding MO. The shades match up, that the phases are the same. So the hydrogen's orbital, its s orbital, and the hybridized orbital of the carbon are coming together, and the area increases for electron flow. But notice that here it's shaded and here it's not. So remember what I just showed you. I said that whenever you have the anti-bonding, that you wind up having, think of it like the lobe, the bigger area is away from the center of the two nuclei. So that's what I'm illustrating over here for you. I'm saying that when this is shaded up here and this is not shaded, then the shade is opposite. It's really big and it's on the opposite side. So notice how that's an anti-bonding MO. This is an AB MO. And we could see the difference, right? So remember, they both exist at the same time. So this carbon here on the right has both a bonding and an anti-bonding MO. And if I could draw one at a time, you really can't draw them both, because then you wouldn't be able to interpret anything. So you have to show one at a time. So it turns out that, and by the way, this is, of course, eclipse, the same idea with staggered. So here's the shaded and shaded matching. That's a bonding MO. Shaded and shaded matching. By the way, it could be shade-shade or unshade-unshade, right? It doesn't matter as long as it's the same. So I happen to do shade-shade. Now, here's a bonding MO for sure. But again, this is an anti-bonding. Here's a shade, and this is unshaded. And so it's a very small area between them. But yet the bigger area is behind the carbon, opposite, away from the middle of the two nuclei. See that? Okay. Now, why do we care about this? Well, what does this show us? And that's what I'm going to do on the next page. Now, if you look at the staggered, it turns out that the reason why a staggered is so stable, and let me just preface this by saying, for many years, we thought it was all about the steric issues, that when the H is on the same side, or any two atoms on the same side, that they're going to start in eclipse, that they have steric problems. But it turns out that's not really the major feature. There's an electronic, remember, steric is different than electronic characteristic. What we're describing now is going to be an electronic characteristic. And it turns out that if you look at the bonding MO of one side, and you draw out the anti-bonding of the other side, so here's the AB MO. Notice that if there are electrons in here, right next door to this is the same shade. So the electrons can actually travel into that orbital that's anti-bonding for the neighbor. See that? It's the same phase. So if the phases are the same and they're neighbors, it's almost like resonance where it shifts over to it. It's not resonance, but it's like resonance. This is called hyperconjugation. So hyperconjugation is the term where a bonding MO electrons can go into the neighbor's anti-bonding MO. This can only happen if the orbitals are the same. They have to be the same phases. Otherwise, it'll cancel out. So in our case, it's perfect. So notice that in the staggered, when one H is up and one H is down, or any atom, I'm just using H's, it's simple. It's a circle instead of another hybridized orbital. But when the opposite of each other, anti or staggered, then the orbital, the electrons in the bonding MO can go over to the neighbor's anti-bonding MO. So the same thing applies with the other neighbor. I just happen to focus in on one. So we're saying that if this is carbon 1 and this is carbon 2, carbon 1 is bonding MO in my drawing, so its electrons go into the anti-bonding MO of 2. But carbon 2 does the same thing. Carbon 2's bond